Perfect. So hello everyone, my name is Anthony Opapari. I'm a PhD student at the University of Michigan in the Laboratory for Progress. And on behalf of myself and my collaborators, so Huiji Zhang, Xiaotong Chen, Jiwei Zhu, Zuren Yu, and Professor Chad Jenkins, we're really happy to be here at the workshop on recovering 6D object pose and to be presenting our work on category level transparent object pose estimation, which we refer to as TransNet. So to motivate this project and how we got interested in it, I'll give some background, which is that we come from the perspective of robotics. And so one scenario that's common in robotics is we'll have a robot that might be tasked with doing some work in a domestic setting, like in this case, viewing this tabletop setting that has a transparent wine glass and also a transparent bowl. And we might want the robot to actually act on the scene. So for example, picking up the wine glass and maybe pouring its contents into the transparent bowl. And this is what we build up to in this project, but currently remains a real challenge for our vision systems to actually support. And the key piece of information that would enable our robot to actually perform this sequence of actions is having knowledge about where the pose of these transparent objects are within the table. So this is kind of like the key piece of information that we're going to try and recover in this project. And so the problem, the real challenge for our vision systems is that transparent objects present at least two kind of key challenges. So on the left-hand side, one challenge is that transparent objects tend to have a lack of distinguishing visual features in the color domain. So in these scenes on the left, you can see that there's many transparent glasswares on these tables, but they're very difficult to see because the light passes straight through them. In addition, commercial depth sensors, which are typically used in state-of-the-art vision algorithms, can fail to actually estimate the true depth of transparent objects. So on the right-hand side, for example, you can see the raw depth, which is what we would get from our sensor, is actually blind to these transparent glass objects on the table. And so the community has been working on approaches to try and address these challenges. So we take inspiration from these works, and this is just a high-level summary. So three kind of broad areas that we've tried to leverage in this project. So first on the left-hand side, so category level opaque object pose estimation has grown recently, which is kind of extending the traditional instance level techniques to work at the category level. But crucially, these works have not targeted transparent objects and those challenges that they present. So recently there has been work done we're trying to kind of leverage at the instance level for transparent objects. So these works tailor typically the neural networks, or at least the algorithms, to try and specifically handle those lack of distinguishing features. And so the insight then that we try and bring in this project is that there were some recent large-scale category-level transparent object pose data sets. In particular, the one that we use in this project is ClearPose, which is also being presented this year at ECCV on Tuesday, to try and move from the instance-level transparent pose estimation to the category level. And so the approach that we then propose is what we call TransNet. So this is a two-stage neural network pipeline that will take input from some vision system and then try and produce as output those pose estimates that could then be used for downstream tasks. So taking a closer look at TransNet, so this is a two-stage neural network architecture. So we assume access to instance-level segmentation as input. So in this project, we used masked RCNN to take a color image as input and then detect the class, so that the category, and also the segmentation masks of every single transparent object within the scene. Those segmentations get fed one by one into the first stage, which tries to correct for the noisy depth estimates. First, by estimating the surface normals within each segmentation mask, and then secondly, by trying to correct for the depth using a depth completion architecture. At that point then, all of the information that we have from our sensor and this depth completion is combined within a generalized point cloud, passed through a transformer-based point former architecture, and then finally we regress the output pose as translation, orthogonal axes, and the scale of each object. So at the kind of output of our network, we'll have a 60 pose estimate for each of the objects within the scene, and also a predicted category label, which came from masked RCNN. And so given this approach, what we then tried to look at, so it's trained in a supervised fashion, and the first kind of result that we were very encouraged by was that it actually does support robotic manipulation effectively. So in this is a robot from our lab performing the grasping and pouring action that we saw earlier, but using the direct output from TransNet for the pose of both both objects. So it knows where to grasp and also where to pour. So based on this encouraging result, we then tried to establish where it is that we fit within the community of work that has been done in this area. And so we compared ourselves numerically to GPV pose, which is one state-of-the-art instance-level pose estimation approach. So this GPV pose network did not specifically try and target transparent objects, but does work at the category level. And so the metrics that we're using here are estimates or are measurements of the accuracy with 60 pose. And so what we found is that generally across our metrics, and in particular for the more strict metrics, so for example, like the 3D IOU at 75%, or the 5 degrees 2 centimeters error in pose, TransNet outperformed GPV pose on this clear pose transparent object data set. And so in conclusion, so in this project we presented TransNet for category level pose estimation. We demonstrated its effectiveness for downstream tasks within robotics, but also in comparison to state-of-the-art baselines. And although I didn't have time to talk about it in this presentation, within our paper we have a set of ablation studies that we would love, or that we think that the community could benefit from to guide future improvements in this area. So we invite you to check out our project webpage or talk to us at the poster session. We're happy to take questions and discuss. Thank you.
Thank you. So, any questions?
I have one question regarding you said that you need instance segmentation first as an input for the network. Mm-hmm. What kind of network do you use for that? Because I imagine like glass objects are already hard on an instance segmentation level to detect. Yeah, so we used mask-RCNN, so we retrained it on the transparent object data set, and we found it's really, really effective. So we don't have, I think, like a ROC curve or those kind of estimates for how effective it was, but it did not, at least in my viewing of the qualitative results, like it never missed an object. It was really, really good at transparent objects. Yeah. Does it work the whole pipeline in real time, or? So we didn't target like optimizing the efficiency. This is all in PyTorch. It's certainly less than a second per object segmentation, but I don't remember if it's like close to 10 frames a second, or I don't remember. Thank you. Thank you.
At the moment, the second step, which is reconstructing the noisy point cloud, this requires like a ground truth depth data set, right?
Mm-hmm. That's right.
So is there any way you can foresee to alleviate this? Because like in industrial cases, you may not always have this available.
Interesting. So there are approaches where you could try and estimate in addition to surface normals and in addition to, well, so we estimate the completed depth, which assumes input from a depth sensor. So are you asking about scenarios where we don't have access to a depth sensor?
Well, so within transparent objects, the depth sensor gives like incorrect results. Mm-hmm. And what you have used now as a training signal is like synthetic data as depth, right? Mm-hmm. So what would you do if you don't have this synthetic depth data available?
I see. That's interesting. That's something we have not thought about. That's because typically in the robotics applications that we consider, we sort of always assume that we do have access to a depth sensor on the robot. That's interesting. Yeah, I'd love to talk about that more at the poster session to see, how we might be able to do that. Thanks.
Yeah, I have one question about the segmentation part. Mm-hmm. So did your both like training and test images show the table with the same tablecloth?
Thank you. So so this ClearPose data set, all of the settings are on a tabletop setting. So but the backgrounds change. So there's a few different tablecloths that were used in that data set.
Okay, and the cloths are different in the training and the test split?
From what I remember, there is some difference, but they're fairly similar. They're quite similar.
Okay.
Yeah.
Yeah, because I was thinking like there are not that many visual clues for the mask RCNN to really segment out the object, right? And I can imagine if you train it on this tablecloth, it remembers the pattern and then can figure out the deformations coming due to the transparent objects. Mm-hmm. But yeah, if it doesn't know the tablecloth, and still can segment the objects well. Yeah, and that's, I would say, quite surprising result. And was it good even like at segmenting different instances
Yeah.
from each other? So it wasn't like overflowing to between like
Right.
covering, let's say, two objects with the same mask or something.
Right, right. And typically it would segment the object that's in front quite well. So it actually was pretty good at actually like the contour, even overlapping with another transparent object behind it. Yeah.
Okay, cool.
Yeah.
Thank you.
Yeah.